Okay, so for number 13, we want to show that A is equal to B if and only if AZ is equal to BZ, where AZ is the set of all integer multiples of A and BZ is the set of all integer multiples of B. And because this is if and only if is a biconditional, we want to show that this implies that and this implies that. So this is going to be a two-part proof. So for part one, we're going to assume let A is equal to B, right? If A is equal to B, this is going to be fairly straightforward, and we need to show that this leads to AZ being equal to BZ. So we're going to say, note that AZ is the set of all integer multiples of A, but A is equal to B. So AZ is the set of integer multiples of B, so AZ is equal to BZ. So this is fairly straight common, right? We're just saying, hey, if, I said straight common, I said this is very straightforward. So this is just saying, hey, if AZ is the set of all integer multiples of A, but A is equal to B, so it means that AZ is also the set of all integer multiples of B, and so AZ is equal to BZ. No big deal here. And so part two, we're going to let AZ equal BZ, and we want to show that A is equal to B, right? So to let AZ be equal to BZ, we want to find some element here and show that that element is also in BZ, and we want to find some element in BZ and show that it is in AZ, and then show that that implies that A is equal to B. So we're going to say A times 1 is equal to A. And the reason that we did this is so we can say, okay, that means that A is an integer multiple, right? Because A times an integer is equal to A. So A belongs to the set AZ. And then we're saying, note that AZ is equal to BZ. And so if they are equal, it means that A belongs to BZ. So if A belongs to BZ, and note that BZ is the set of all integer multiples of B, right? So note that BZ contains integer multiple of B. So it means that then that B is going to be equal to some A times some integer, right? So we're going to say here that so A is going to be equal to some B times D, where D is an integer. So we're saying, hey, if A is in the set BZ, it means that A must be an integer multiple of B, right? Because that's how the set is defined. Okay, so now we're going to do it the other way around. We're going to say B times 1 is equal to B. So because B times 1 is an integer multiple of B, so B belongs to BZ, right? Let me just make this better. Yeah. Well, if B belongs to BZ, BZ is going to be equal to AZ. So it means that B belongs to AZ. And similarly, AZ contains integer multiples of A, of A. So if B is in AZ, B must be an integer multiple of A, right? So B is going to be equal to, let's see, AC for some integer C. Oops, I wrote enter, but I meant integer. Integer C. So now notice here what we have. We have that A is equal to BD, right? Because A is in the set of integer multiples of B. And we have that B is equal to AC because B is in the set of integer multiples of A. So if this is true, let's then compare it. So we have here that, note that B is equal to AC and A is going to be equal to BD, right? So if A is equal to BD, it means that then A is going to be, wherever I have B, so wherever I have this B here, I'm going to put in this definition here. So we have that A is going to be equal to, B is AC, right? So it's going to be AC times D. And so once I have that A is equal to AC times D, if I divide by both sides by A, so 1 is equal to CD, right? So from here, we have that 1 is equal to CD, so 1 divided by C is equal to D. Now note that D is an integer, right? We said that where D is an integer, we define D to be an integer. So for D to be an integer, it means that, so C is equal to 1 or C is equal to -1. Because if it were some other number, like if it were 2, then 1 divided by 2 is equal to D, and D would not be an integer. Note that B is equal to AC and AB belong to the set of natural numbers. And we have that AB belong to the set of natural numbers because this is given for natural number A, right? So if B is equal to AC and A and B are natural numbers, it means that A and B are positive. So C is equal to 1. So if C is equal to 1, thus A is equal to B. Because if we plug in here 1, we're going to get that A is equal to B. And that is it for our part 2. So just to recap what we did in part 2, we said that, hey, A times 1 is equal to A, so A must be in the set AZ, but AZ is equal to BZ, so A must be in the set BZ. So if it's in the set BZ, it means that it's an integer multiple of B, right? So A is equal to BD here. And we did the same thing for B. We said that B times 1 is equal to B, so that's in the set BZ. And BZ is equal to AZ, so that's in the set AZ. So if B is in the set AZ, it means that B is an integer multiple of A, so B is equal to AC. And then we just plugged B into that equation and showed that, hey, that must mean then that C is equal to 1. So if C is equal to 1, it means that B is equal to A. And that is it for part 2.